Okay, so good morning. I hope you have seen my email and my message on the website about the recovery lesson we are going to have today at 2:30 in room 2I, which is here. It's going to be 1 hour and a half. That's because I'm going to skip one class. I'll let you know later. One Thursday I will not be available, so we need to recover some hours. Very likely we will have one lab experience, which is something that was not meant to be before when we started the class, but I have a PhD student that is helping me in planning that. So it should be one 3-hour class in a lab. I will let you know when. It's going to be in December. And of course, you will have classes in which we will explain what we are going to do there and why and so on and so forth. So it will be one additional lab exceeding the normal class hours. It will be Wednesday 2:30. I checked on your timetable. This is that there is no overlap with other classes, if I'm not wrong. So it's going to be Wednesday from 2:30 p.m. up to 5:30. Okay. I will give you more details about that, but I want to announce it now just because you know. There will be not a direct commitment within the exam. I mean, I'm not planning to ask you questions about that lab experience, but of course, since we will have some classes that will prepare you to the lab experience, for what concerns that part is fully included in the examination part of the exam. Okay, any question about that? Any doubt? Okay, so if I'm not wrong, we ended up basically here last class. If I'm wrong, just tell me, in which we have stated in a very general way what we mean by, at least in this class, by quality of service problem, which is a design problem, in which we assume that we have given a network topology in terms of nodes, link speed, and connection among nodes, the traffic characterization generated by the user and the user behavior, and we would like to obtain jointly two things. One is to have a reasonably high network utilization, and at the same time being able to provide some type of QoS for each user connection flow call, or whatever you want to call it. So this definition is very vague because you have many options. For example, in terms of traffic characterization, you may require a very detailed or a very weak traffic characterization. In terms of what you want to guarantee in terms of QoS, you have a very wide variety of options, so it's a very general design. And the important concept is that only when you want to obtain these two goals jointly, the problem becomes kind of complex. If you want just care about QoS, we have solutions available. One main example is the telephone network, in which you have a very good quality in terms of user perception. But a drawback is that the network utilization is very low. If we care about network utilization, we have a packet switching with datagram service, which is very good potentially to allow you to use a lot of resources in a very efficient way because there is no allocation. But at the same time, we have very much difficult in providing QoS. And the so-called over-provisioning approach, which is the approach that people that load the packet switching with datagram try to pursue, is the idea of putting so many resources that you have no problem of quality of service by definition. Because when you have enough resources, of course, everybody will be satisfied, and so satisfied, and you don't have any issue in controlling and managing and providing this amount of resources to this set of users and this amount of resources to another user. So that's an approach that we don't want to follow, and this approach, the drawback of this approach is, of course, that it costs a lot. Over-provisioning means putting a lot of resources, a huge amount of resources, and that translates in very large costs that we assume we are not able to face. Of course, if you can face this approach, that's going to be a good idea because that makes the network management and control very, very simple, and at the same time, it ensures that you have a very high satisfaction from the user perspective. So in this context, I think that we have not discussed this yet. There are some design issues that I want to start to introduce now, and how mechanisms that we can exploit to obtain quality of service. So the first observation is that we'll see several types of algorithms or tools, if you prefer, and while we describe them, we'll understand very clearly that they operate at a very different time scale. Okay? Some control algorithms run at a very short time scale. For example, any algorithm that is dealing with packet management. Other type of algorithms may require a much longer time scale, and of course the time scale at which you have to run the algorithm has an implication in terms of algorithm complexity. Because if your time scale is very relaxed, you can envision that you can run fairly optimal or very complex algorithms to obtain your goal, because you have a lot of time to run them. On the other side, if you need to run on a very short time scale, that's not possible. So there will be also the issue of making a compromise between the theoretical property of a given algorithm, and the ability to implement that at that time scale. So we will very often look for heuristic suboptimal solutions, but that are implementable within that time bound. Okay? If you come out with a very nice algorithm, perfect, optimal, you can demonstrate that, but then in order to run it, you will need a time that you don't have in real network. That's completely useless. I mean, it can be used as a comparison, but is not practical solution. So that's why it's very important to keep in mind this different time scale over which the algorithms are running. And there is an example here. Well, one tool that is important to obtain QoS is the so-called network design and planning, which is related to resource deployment, which is something that we are taking as granted, if you remember the previous slide, when we define the problem of providing QoS. We have stated that we assume that the network topology is given in terms of node, connection, and link speed, and that's the network capacity. How many resources we have put in place, okay? But of course, the initial step is to design and to make a decision on how many resources you want to put on your network, and that's the first element that you will have, and that will have a consequence on the QoS perceived by the user. And so that's called network design and planning. So it's about resource deployment. Now, this is running on a very large time scale. Okay? You don't design a network every 2 weeks. You design your network once every 6 months, every year, every 2 years, or something like that. If you start thinking about also not only the first initial deployment, but the more typical problem that providers have to face, which is redesigning and replanning, which means adapting an existing network, modifying it. So that's called redesign or replanning. That again is running on a little bit shorter time scale, but still very large. Okay? You typically replan every few weeks or something like that in general. Maybe a little bit longer. So that implies that you have a significant amount of time, and that implies that you can use significantly complex algorithms, because even if this algorithm requires few hours to run, who cares? Okay, you run it every month or something like that, so even if you run it by 1 day, that's perfectly fine to get a good solution. How network design and planning are running, we will see something about that. That's not the course which is facing in a very deep way this type of aspect. There are more modeling-oriented courses in which you will see technique used to do network design and planning. And basically, these are done on the basis of 2 information. One is the traffic estimate. You need to know something about your user needs, right? If you want to plan something, well, the first thing is to, okay, which is the problem I want to solve, right? Any type of planning scheme, right? When you want to design a road system, you need to ask yourself, okay, how much traffic I envision there will be from here to there and from there to here and so on and so forth, right? You need traffic estimation. And on the other hand, the other important aspect that will guide your decision process in designing or redesigning and planning is the cost. how much money is available to put resources in place. Right? If you don't have cost bounds, you have the nodes, you know where you want to put the nodes. Where you have customers, you will have a node, right, for sure, because you need to collect the traffic generated by your customers. And the obvious solution, which is optimal from any perspective, it will be to connect any node with any other node in your network with a direct link. You know that, right? The full mesh is the best solution in terms of efficiency, amount of resources. That's the maximum amount of resources you can put there, right? On the other hand, that's very, very costly. So you have to balance these two things. And while we are doing network design and planning, we will exploit also routing criteria, because the path followed by the traffic has an important implication in terms of how much capacity do we need, and also what's called traffic engineering, which is related to routing, is a sophisticated way of making choice about which is the best route, not necessarily the shortest one, but according to some other criteria, you may select another route, okay? When you drive from city A to city B, normally you will select, well, the road that gives you the highest speed, so that's the highway, but if you know that the highway is congested, maybe you can divert and select another road, right? That's called traffic engineering. So you change your routing choice depending on the network status, okay? So that's one building block. Then we have another tool, which is important, which is the network management. We will see what does network management mean. Roughly speaking, it means running a network. So having a network and making it operate daily, on a daily basis or an hourly basis. So that implies measurements. Why measurements? Because you want to know what's going to happen, what's happening actually, not what's going to happen. You want to know exactly what's happening. So measurement is monitoring, checking what's happening. You have issues related to fault management, dealing with when something goes wrong, what we have to do, okay? That goes through the protection and restoration algorithms. So these are all algorithms that we will see. Protection means put in place mechanisms that allows you to recover if a fault happens. We have seen an example of that when we discussed about the properties of a bidirectional ring topology, SDH, if you remember something about that. We say that, okay, given that SDH is based on a bidirectional ring topology, we have an automatic protection system against faults, which restore the connectivity of the ring through a unidirectional ring. That's protection, and restoration is instead what you do when you want to restore. So when the fault is recovered, the time needed and the procedure you follow to put again your network to operate in the proper fashion. And again, network management is running on very different time scale with respect to the previous one, right? Network management is run continuously. So you may have measurements which are running on a very short time-based scale, depending what you measure. If you want to measure the packet rate, you need to run it at packet rate. If you want to measure an average load every 1 hour, of course it's running periodically every 1 hour, and so on and so forth. And sometimes redesign and replanning is also called network management in some sense. When you adapt, you modify your network architecture is a sort of network management, right? You discover that there is an issue and you want to solve it. So it's between the replanning and redesign and management. It depends on which perspective you want to take. Then there are algorithms that are running at the connection management time scale. Now the connection management time scale is in the order of seconds, tens of seconds, hundreds of seconds, okay? And an example of that is, for example, when you want to block a phone call, right? When you open a phone call, you run a lot of procedures to select the path, to ensure that you have enough resources, to allocate the resources, to manage the connection, and then to release everything. So that's connection management time scale, okay? Here the time scale is much reduced, okay? You have to make a decision about a connection typically in few seconds or maybe less than that. So here we need algorithms that are faster, and typically the need of being fast implies that they cannot be so optimal. And finally, any algorithm that we see which is running at the data unit transport, so everything that is dealing with the packet, each packet, you have to do something packet by packet, buffering, for example. That must be fast. The packet transmission time today in wired networks is very short because we have very high speed link. The packet transmission time is typically hundreds of nanoseconds or something like that. So, and we have to run our buffer management and many other things that we will see on every packet. on every packet. So that implies that those algorithms should be very, very fast. Typically, they must be implemented in hardware. Otherwise, you will not be able to sustain that line rate. So you see that there is a very different level of complexity, the very different level of time scale, okay, and very different level of implementation issues. Okay, typically, while you move down in this slide, you reduce the time scale, you reduce the complexity of the algorithm, and you make it, the implementation stuff, more complex and more hardware-oriented instead of more software-oriented. Okay, while you move down in this slide. Is it clear? Okay. This set of slides typically seems to be a little bit vague, but it's very important to put order in terms of taxonomy about what we are going to see later. So maybe now you will not fully understand all the details, but when the class, all of the classes is going to be over, go back to this set of slides because they will allow you and make it easier for you to classify things in a proper way, and that's very, very important also to remember them. So we will assume that the network has already been designed and is properly managed. So from now on, for a significant part of the class, we will assume that we have a network that has been designed, so we know the resources, and we assume that the network is properly managed, so we don't have to deal with any management issue. Okay? So in other words, the available resources are given. It's something that we cannot play in this phase. And we will mainly study algorithms which are operating at the two following timescales, which are connection management based and packet based. So most of the time from now on will be devoted to algorithms that are running at a very short time scale of the packet based or the connection based. Sometimes this is also named traffic control. So you want to control the traffic in order to guarantee something. One important aspect, very important, is what we mean by connection. If you go back and review what I said during all of these classes, I've been using different terms. I've been talked about connection, I talked about call, I talked about flow, and possibly some other. Okay. Now, what a connection is very important. We have to define what a connection is. Now, for example, in circuit switching, phone-based network, what a connection is very easy. It's a phone call, full stop. Okay? And everything is treated as phone calls. Even when you send a fax, from the network perspective, that's a phone call. You have no idea about the fact that it's a fax. Okay? So in that case, it's very clear to see what a connection is. When you start discussing about packet networks, what a connection is, it has to be defined. From the packet switching with datagram service perspective, the connection is the packet, because that's the only entity over which you operate. From the packet switching with virtual circuit service, the connection is, well, the virtual circuit, or maybe the group of virtual circuit. So you start to see that when you want to define what a connection is, we have a degree of freedom as the network manager to see, okay, this is a network connection flow, whatever you want to call it. Okay, so if you aggregate a lot, you will see very few flows. You may say, okay, for me the flow is everything which is going from this side to this side. I may have 100 users here, 100 users there, so that will be potentially 100 connections. I don't care, I treat all of them together. That's one way of defining a flow. The other way is to say, no, I want to treat them independently. I will see 100 flows. So the definition of what a flow is has an important impact on the network complexity and on the quality that you provide, because you will be able to provide quality to each connection, to each flow. Now, what the flow is has also an implication of what the user will see. So if from my perspective this 100 connection is a single flow, I'm grouping all of them together, well, I will be able to provide quality, some sort of quality, we have to define which, to the aggregation, to the global flow, but not to the single connection within the flow. If instead, if I'm dealing with this 100 connection independently in my network, I can provide different QS to each connection. So what a user connection is and how it is mapped to a network connection has a big implication. Our goal is to provide a given user-to-user connection. But we have to define what a connection is in my network architecture. So that's a very important thing. In some cases, it's trivial. In some cases, it is obvious. In some other cases, it should be defined. And depending on how you define it, you will get different properties. OK? Sometimes this problem is called data classification problem. It's the concept of defining what is a flow. Let's take the example of the internet. One way of defining a flow is everything is going from this IP to this IP as a single flow. That's one way of defining a flow, right? Another way is to say, no, every single TCP connection going from here to there is a different connection or flow or whatever you want to call it. And that makes a different granularity, different number of connections you have to deal with, etc., etc. Is it clear? So that's a very important thing. This will be one of the very important elements when we will design the network architecture. So we will see many tools, and then depending on which tool you are going to use, which hypothesis you will make, which definition you will have a given QoS model in your network. And one key element is what is the flow. Our goal will be to provide different quality potential to different flows. But before doing that, you need to define what a flow is from your perspective. Okay? Another important general concept is that there are two main, again, this is the taxonomy, two main approaches or traffic control principles which are contrasting and that are typically used jointly in a network architecture. The first family is the so-called preventive control, and the second family is called reactive control. Now, if you remember something about what we have revised about multiple access protocols, we had something similar there because we had two different approaches. One was to prevent any problem in our shared medium, and we have not discussed that deeply. Okay, so we want to ensure a priori that there is no overlapping of transmission. So we have described very informally the token-based approach, etc. And the other one was called reactive. I'm doing nothing, but then if a problem happens, I react and do something. And here is something very, very similar. We have a set of families of algorithms which are typically preventive, are run before, for example, you generate the traffic. So they are typically executed at the network boundary, what is called network ingress, where the user is generating data and where the network is starting to see the data. And the idea is that you want to run and control your network in such a tight way that you want to avoid the insurgence of any problem within the network. The problem is typically the congestion. So the idea of preventive approach is to say, okay, I'm controlling what's happening at the border of the network so well that as a consequence, within the network, I will never have problems. Okay? That's the idea, the general idea of preventive approach. And when all of the algorithms about QoS provisioning were being defined in the 90s, more or less, early 90s, most of the approaches were following this idea. Okay, we want to have a tight network control so that we ensure that we avoid, everybody's looking for me today, so that we avoid any issue. Now, is it working? Yes and no. I mean, if you really want to do that, you can. You can even rely only on preventive control if you wish. But typically, this will prevent you from obtaining a good utilization. And a good example of that is circuit switching. Circuit switching, you control everything, you know everything about the user traffic, you guarantee a priori with a deterministic way everything, and you get very good quality, right? But the utilization is very low. So that's the drawback of preventive approaches. On the other hand, the reactive approach is following the other approach. So when there is something bad which happens, which is here is summarized as congestion, of course you can try to react earlier than congestion. You may say, no, I'm going to react when the load is 60% or something like that. But I'm going to react only if something bad happens. Okay? Now this typically is an approach which alone may probably prevent from reaching a critical congestion scenario in your network, but it makes it difficult to guarantee quality, especially if you want to guarantee the quality a priori. So typically you will see that in a given network architecture, as I said, you can combine as you wish many different elements, but you will typically find both preventive and reactive control, maybe for different sort of users, maybe for different type of traffic. But typically you will need both of them if you want to obtain jointly those two goals, QoS provisioning and high utilization. So we will need both preventive and reactive control. Some algorithms are typically preventive, some other algorithms are typically reactive, some algorithms are preventive but can become reactive if you accept to change over time your decision. So they may become slightly reactive. That depends on whether you will accept or not to change your decision, your prior decision. Now, having said that, I want to go through all of the algorithms we will see in the class. And before doing that, I want to tell you which are the essential elements that we need in our network to do what we have set up to now, which means providing a guaranteed negotiable QoS per user flow, connection, call, whatever you want to call it, and at the same time keeping an eye on the network utilization. We cannot say that the network utilization we don't care. So the first obvious element is to have a connection-oriented network, and there are many slides we are going to go through all of them to describe it. The first element we need, so connection-oriented means the ability of identifying the connection in your network, basically. Okay? If I'm not able to identify what a connection is in my network, it's going to be difficult to do anything about that. So connection identification is important. Second point, user-to-network service interface, over which I'm asking the user to characterize the traffic. You have to tell me something. Okay? You are the user, you want to generate, you want to have some guarantees from the network, okay, but you have to tell me what you are going to do. Because if I have no idea about what you are going to do, which type of traffic you are going to inject, how can I guarantee you something? So it's fairly obvious that we need that. So we have a traffic characterization and the QoS negotiation process which is needed. I'm not saying that this should be very detailed or that should be very that's up to you. That depends on the network architecture you have in mind. But you need this element, some sort of information about the user behavior. Then you need to do some resource allocation. Now there is an important principle. When you have a given amount of resources, the more you partition them, the higher the probability that you will not be able to use them in a very efficient way. Okay, that's absolutely true in general, any system. When you do a partitioning of resources, okay, you may deteriorate the overall utilization of that resource, for sure. You are not going to do better than the case in which you have no partitioning. That's for sure, but on the other hand, if you don't do some partitioning, it's going to be very difficult to guarantee something to the different flows, connection, calls, users. So that's an element that we will need. Some sort of resource allocation algorithm. And mainly, we are going to allocate bitrate and the buffer. Okay? And then we need algorithms. We need algorithms to control the traffic. And type of algorithms that we need are called, well, for sure we need some routing algorithm. We have to choose the path over which to run our traffic. And we have to make sure that on that path, we have enough resources to satisfy your requirements, right? And that's the CAC, connection or call admission control, which is basically following the very trivial principle that since I have a finite amount of resources, for sure the amount of resources available is finite, I need to ensure that the number of users that at the same time are trying to get a slice of these resources is bounded. Because if you don't bound the number of users, there will be no hope in providing something. Very trivial, okay, very obvious. So sooner or later, depending on the number of users you have and the number of resources that you have in place, you may need to say to some user no. Because otherwise, if you don't do that, there is no hope. If the number of users becomes unbounded, the amount of resources that each user is getting is becomes negligible, trivial. We need some scheduling and buffer management because we have to make a choice. If we have limited resources again, what we are going to drop? I may have a choice among many packets. Which is the most clever choice? That's buffer management. And scheduling means, okay, among all of the packets that I was able to store, which one is more important? Which one should get out first from this node to ensure that my users are satisfied? Okay? Then we will need some conformance verification algorithm, or if you prefer, some traffic shaping to adapt my traffic. Because if you ask the user to tell what's going to do to make your computation and to ensure something, then you have to guarantee that the user is not doing worse than that. Because if I ask you how much traffic you are going to generate, and he's telling me I'm going to generate 1 megabit, and then in reality is going to generate 10, not only is going to destroy his behavior, of course, because I've allocated resources for 1 and you are injecting 10, but you may risk to create problems to any other users sharing with you some resources. So you need to control what the user is going to do. And that's called traffic policing or conformance verification. You need to be conformant to what you have taught me. And finally, if all of the other algorithms are not working, then you may need congestion control. Congestion control is a mean to get out of a serious problem in the network, which is the congestion problem. Okay, you need to avoid it, you need to get out of it as soon as possible, because congestion implies losses, implies retransmission, implies a further increase in the traffic load, etc., etc., etc. So if you want to run a network which is providing some quality, to be completely honest, congestion should never happen. Because whenever you have a congestion problem, by definition, the quality that you are going to provide is not satisfactory for your users. So you cannot say, well, if there is congestion, who cares? Sooner or later we get out. No, we want to run a network with a different characteristic, and that's the only way of doing that is to run some congestion control algorithm. So we will need all of those elements to hope to reach our goals. Now the game will be to define for all of those elements which specific choice we are going to make in our network architecture. And of course the choices are not uncorrelated. They are not independent. Okay? Just to give you an example, the flow definition, what is a connection for you as an implication of the CAC in terms of how frequently you have to run your CAC. Because if in the previous example, right, this large connection between two nodes, two LANs, two sites, I have one single flow from the network perspective, everything going from here to there, I'm putting together, that's one connection, and you have to deal with that once every, I don't know, once every day, something like that. Instead, if you are dealing with all of the connections generated by a single pair of users independently, of course, you have much more connections, many more connections, and you have to deal and you run your CAC much more frequently. So you see that things are not completely independent. You have to take care about everything together. So that's why I will repeat this many, many times. We will see every single element in isolation, but then at the end, you have to start thinking about the correlation and the implication between the different algorithms, the different choices that you have made, to have a full picture about what's going to happen in your network. Okay? So that's very important to remember and keep in mind. So some more details, if you don't have questions right now. I bet that all of you are still sleeping. Yes, okay. So some more details about each of those elements now. Of course, we will have more time and we will devote more time to any of them later, but just to put some point here. So why it's important to have a connection-oriented network approach? For the reason that we need to identify what a connection is in my network, and my network means in all the network elements over which we are going to run our control algorithms. So I want to control the user traffic, that's the principle. And I want to control the user traffic per connection, per flow, per call, whatever you want to call it. Now, I need to run some control algorithms in my network elements. It can be a network boundary, it can be in each network node, it can be in each network transmitter on a link, whatever. But at the end, I need to identify in all of those elements which are running these algorithms what a connection is. If I have no idea about what a connection is, I cannot run anything. So that's why it's important to have a connection-oriented network. So I need to know the path over which the packets are sent in order to hope to control this flow, this connection. If instead you have packets generated which belong to the same user flow, or something that I define as a network to the flow, and these packets are spread out randomly on any possible path, how can I control it? How can I guarantee anything? So that's the notion of over which path these packets are going to be sent. It's very important to start to hope to do something. So that's why we need either a circuit switching approach in which we know exactly which is the path, which is fixed forever, or a packet switching with the virtual circuit service, or something similar to that. In both cases, we fix the path, and we know that all of the packets belonging to this flow are going to go over this path, are going to be sent over this set of links, are going to be managed by this set of nodes. Okay? And so I can operate on that path, on all of those links, on all of the nodes, if I want to do that, and I want to do something for this connection. Clear? At the other hand, if you remember, we have said that we have two joint objectives. So this holds for what concerns the ability to provide QoS. If you want to obtain high utilization, we need to have packet switching. Packet switching is a way of implementing what? Statistical multiplexing. I give more to who needs more. I give less to who needs less. I need something which is dynamic. It's not predefined, it's not deterministic, it's statistically assignment of resources. So I will need packet switching. As a consequence, the most suited technology to obtain our goals is something which is packet switching with virtual circuit service, or something that looks like that. Okay? So we need to have a packet switching. We need to have not a full allocation of resources which is deterministic, because otherwise we will not have any sharing. And if we don't have any sharing, we will not have reasonable utilization. Okay? So that's why broadband ISDN is coming out to be as the most natural choice for this type of problem, because in broadband ISDN we have a packet switching process and we have virtual circuit service. So we have all of the features which are available here. And indeed, in the internet, which is instead packet switching with datagram, in order to provide and to extend the internet basic model to provide QoS, you will see that we need to have a modification of the internet paradigm that will somehow allows us to identify packets as belonging to a flow within the network. There are different ways of doing that, but it's some sort of virtual circuit definition or flow identification within the network in order to provide some quality. Okay? Traffic control, the basic concept here is that I need to know something about what the user is going to do in order to be able to control it. Okay? Now, in principle, the more you know about user behavior, the better it is. You have a lot of knowledge, so you can control better, right? That's, again, intuition. That's common sense. That's true, but with a given limitation, which is due to the complexity. Remember that we need to run algorithms in a reasonable time scale. So even if you know, suppose that you knew everything about user behavior, just perfectly well known. I know exactly how many packets you will generate of which size at which time. That's basically unmanageable. It's too complex information. I cannot handle this complexity in a real network. Okay? So, yeah, in principle, the more you know, the better it is, but there is a limitation. You have to balance between information and ability of using this information at that time scale. And the time scale here is the packet time scale, because you need to control the user traffic at the packet level. and that time scale is very, very short. Okay? So we will need to find a reasonable compromise between the need of knowing what the user is going to do and the need of describing this knowledge in a number of parameters which is limited that will allow us to do some reasonable computation in short time. Otherwise, this process is going to be useless. So we need to define what is called the service interface. And over this service interface between the user and the network, you will have a traffic characterization process on the one end, the user that declares to you what is going to do, and the QoS parameter negotiation, which is the user which is asking the network to provide something. Okay? This type of service interface can be defined on a contract basis. So you sign a contract and you say that, okay, I need to have an access of 10 megabits per second, 24 hours a day. That's a contract-based approach. You know that the user is not going to generate more than 10. That's what, and maybe the QoS that you require is the availability of this bit rate 24 hours days. That's one possible approach, right? That's one possible solution. It's not a very sophisticated model of quality of service. It's just on the aggregation of the user traffic. That's one approach. Or you may have a network architecture in which these two things are declared, the traffic characterization, and negotiated, the QoS, on a call basis. Whenever you wake up and you want to do something, you have to declare how you generate the traffic, and you have to ask something about this quality. This, of course, is much more flexible, right? Because a user may generate a FTP file transfer protocol, a file transfer application, in which, of course, the requirements are of a given type, and then you wake up later and you want to make a video conference, and the requirements are going to be very different, right, for the same user. So clearly, having this possibility of defining a service interface on a call basis, whatever a call means, it's much more flexible. At the same time, it means that it's much more complex to handle. Okay? But we need something like that. Now, if you think about the plain old telephone system, the telephone network, we have it. This is basically on a contract basis. It's not declared explicitly because it's completely implicit. The agreement in that network is that any user is going to generate exactly that type of traffic, which is a CBR connection, constant bit rate, 8 bits per sample every 125 microseconds. That's how a user is going to behave. There is no negotiation which is possible. That's the traffic characterization. Is connected with the network architecture definition. You have no choice. That's it. And you have so many choice, so little choice, that it's the network itself that is sampling your traffic and is generating in that way. It's not even the user that is doing that. The user is generating an analog signal, and then the first node in the network is sampling it. And you generate that type of traffic, which is CBR, with a data size of 8 bits every 125 microseconds, which turns out to be a 64 kilobit per second bit rate channel. Okay? So it's on a contract basis. It's not negotiated call by call, and it's not explicit, it's implicit. There is no signaling, because by definition it's like that. Okay? Clear? In the internet there is no service interface. You wake up and you do whatever you want, and nobody's asking you anything. You open a connection, and it may be a TCP connection for a file transfer, for a web download, or for an email transfer, or whatever. You don't know. You can do whatever. You don't declare anything. You just wake up and try to send packets from here to some IP destination address, and that's it. There is nothing else. So there is no traffic characterization, but at the same time, there is no possibility of asking for anything. Sorry, I forgot for the plain old telephone system, not only the traffic characterization is implicit, also the QoS requirements are standardized. The QoS requirements are fixed bit rate and minimum possible end-to-end delay, which is the propagation delay only. Okay, so not only the traffic characterization, but I forgot to discuss about the QoS part. In the internet, there is no service interface, so you have no idea about what the users are going to do. but at the same time, you don't give the user any possibility of asking for sound quality. There is no possibility of doing that. You cannot tell the internet, okay, I want to open a video conference, now I need 2 megabits per second from here to here. That's not possible. You cannot do that. Okay? What about frame relay? Well, we have seen a little about that. We will see much more. But in frame relay, basically, we have a negotiable QoS and a negotiable traffic characterization, in the sense that the set of parameters that you must use to describe your traffic is standardized. The values assumed by this parameter is negotiable. You can change it. And the quality of service is somehow negotiable. It's mainly bitrate oriented only. So you can typically negotiate only the bitrate, but you can negotiate that. Potentially, you could do that on a call basis. Remember that making this call basis assumption implies that you must have signaling protocols. All of the signaling part, if you remember when we have seen the protocol architecture, which was 3-dimensional in broadband ISDN, you remember that we had 3 planes. Who remembers the name of the 3 planes and the functions? User plane for the data transport, control for what? Basically for signaling, and management for controlling, etc. Now the signaling goes to the control plane, and signaling is needed exactly when you want to negotiate something on a call basis. Signaling is typically needed whenever you want, for example, to open a connection, even if you don't have QoS requirements. In the cell phone network, you have the signaling, right? You have to tell the network, I want to talk with that guy with this number. That's the signaling in the telephone network. Normally, in the signaling phase, you have also all of the features of QoS requirements negotiation and traffic characterization declaration. So that's possible in frame relay. All of the signaling standards have been produced and are available. Practically, very little of this has been used. So normally, when you have a frame relay access, you normally have this negotiation process on a contract basis. So it's not on a call by call. So you have an access as a user, and you will say, okay, I want an access at 12 megabits per second, and then that's it, basically, because the only requirement that you can declare is bitrate oriented. There is no delay, no losses, nothing like that. Okay? And there is also an implicit traffic characterization declaration, which is related to the QoS requirement in that case. In the broadband ISDN case, as we will see, this service interface is available. The approach is that everything is fully negotiable on a call basis. So there is a huge set of signaling standards that have been designed and proposed and standardized, in which you have a traffic contract. And of course, you can do that on a contract basis if you wish, but also on a call-by-call basis. Okay? And the internet extended to support QoS, which is not the standard internet, this typically is negotiable. So this service interface is available, is negotiable typically on a contract basis through what is called an SLA, service level agreement. It's called traffic contract in broadband ISDN. It's called SLA in the internet, but is the same concept. And normally it's much more limited with respect to the ability that you have to negotiate with respect to the broadband ISDN case. And normally it's mainly run on a contract basis. Okay? So you see that there are different complexity and flexibility levels which may be available, as we have already seen. Yes? Now, the answer is yes and no. You will see later, when we discuss about extension of the internet to provide QoS, there are 2 main approaches. In one approach, we mainly rely on preventive control, and we need signaling to ensure that we allocate resources, but this is not mainly running on the basis of priorities, as you were stating. The other approach is instead exploiting priorities. Okay? And we see that these are 2 typical things that we will do on the one hand, and on the other, there are 2 different possibilities. which are also available, for example, in FriendRelay and Broadband ASDN. So you can have a mix-up of the two. So this is one possibility, but that's not the only one. Okay. Any further question? Okay. Now, the third approach is resource allocation. Now, which are the resources we are talking about? Well, mainly two types of resources, which are bit rate over transmission links and buffering nodes. These are the two main resources we have to allocate. Now, this allocation can run and can be managed at different time scale and a different level of complexity. You may have a contract basis allocation, which is sometimes also called booking. So you reserve something in advance. Typically, this is done mainly on bit rate. So when you create a permanent connection, for example, from A to B, you set up a path, and this permanent connection requires k megabit per second. You will need to set apart k megabit per second on any link on the path to ensure that these k megabit per second are available. Okay? So that's a contract-based approach, and which is sometimes called booking or trunking or something like that. Or you can do that on a call basis. So whenever you open a call, you ask for a given bitrate guarantees, and you do the same process that I described previously for each call independently. Okay? And of course, when you do that on a contract basis, you sign the contract only if the resources are available. Whereas when you do that on a call basis, resources may be available or not, depending on the current network status, so you don't know in advance. So in a contract basis, the blocking is by definition not existing, because if there is a blocking, you will not sign the contract. On the call basis, the blocking becomes possible. And you may also have resource allocation on a packet-by-packet basis, especially of buffers. Okay? You may have buffer allocation also on a call basis or on a trunking basis if you wish. It's a little bit less common. And this allocation may be exclusive, so that implies that these resources are dedicated. Think about the circuit switching approach. In the circuit switching approach, one slot every frame is devoted to a given connection, right? And that's a transmission link capacity which is dedicated to a given call in a predefined way when you open the call. Okay, you think about the SDH frame, which I'm sure all of you remember by memory, right? Every field, if you remember that, that was a slot-based frame definition, and we had control slots, right, for management purposes, etc., and those are reserved on a contract basis, right? That's the standard that tells you that this slot is reserved, for example, for management calls. So you have one phone call for management purposes, etc., etc. Or the allocation can be shared. So you allocate a given amount of resources to a subset of calls, which for some reason are willing to share some resources. Okay? These are essential elements to ensure that you are able to provide some quality. Few minutes more because we break. Now, let's start with a general discussion about algorithms, and we will start with CAC and routing. So what CAC and routing is? Well, routing is a path selection to route a connection, not to router a connection. Sorry, there is a mistake here. This is a path selection to route a connection. Okay? And this selection is actually done also in normal networks, right? In any network, you do need to have a routing process. In this case, if you wish, the routing property can be extended, can be made more sophisticated, but also more complex, according to what is called QS routing based. So what I said before, in the routing, normally you say, okay, I want to go from Torino to Genova, which is the best path. I have to drive through this highway up to, don't remember the place, Alessandria, and then I have to go down on the A26 to reach Genova, okay? And that's normal routing. Okay? That's the best path. QS-based routing may tell you, wait, pay attention, there is a congestion point here, and that's a huge congestion. and you do that dynamically, and you change your routing decision. So it's the QoS-based routing, because my objective was not to go on the more comfortable way, which is a three-lane highway, but on the fastest one. And the fastest one now is not that one. I have to go on another road, okay, because there is a huge blocking or a huge congestion traffic. That's a QoS-based routing. You made the routing choice not only on the basis of topology information, but on the basis of quality of the link, which is dynamically changing. Of course, this makes the problem much more complex, because it requires a more complex monitoring. In the routing case, you need only to know whether this link is available. And that's it. So only under default, you change your topology. In QoS-based routing, all of the links which do not satisfy a given QoS bound disappear from your topology, because you cannot use them. And this is, of course, much more dynamic. That's the QoS routing approach. Okay? Now, once you have selected the path, you have to make sure that you have enough resources on every link on that path to satisfy your call. And this is what typically does the connection admission control problem. You may say, well, but I can solve this at the routing level, because if I have a routing which is so sophisticated that gives me a perfect picture of what's happening now in my network, I can select a path which by definition already has enough resources. True, but that requires a huge complex QoS routing scheme, which is typically not feasible. So normally the routing should be a little bit simplified. So we'll give you a given set of tentative paths, potential paths that may be okay, but you are not exactly sure whether now they are okay or not. And then once you select one of them, you go on that path link by link, and you will run a CAC algorithm on each node on that output link to ensure that you have enough resources to satisfy the quality required by this call. So you run this call by call. Now, what the call is, we have to define. So the CAC is determining whether to accept a connection or not. That's the outcome of your CAC. So the outcome of the QoS routing is a path, or a set of paths, more than one if more than one is available. On each of those paths, you need to run a CAC whose outcome is binary, accept or not the call. Depending on what? Depending on the path that you are examining, depending on the traffic characterization, because that depends on how the user is going to generate the traffic, whether I have to accept the call or not, which are the QoS requests. So it's different whether you require 10 megabit or 100 megabit or 1 millisecond end-to-end delay. These are different QoS requirements, which may have different implication in the amount of resources I need to satisfy this requirement. So it depends on the path, it depends on the traffic characterization, it depends on the QoS requirements, and it depends on the network status at that time. Okay? How many resources are available? And of course, it's not written here, but the assumption is that if you accept the call, you need to set apart the amount of resources that you have designed to be enough to satisfy the QoS requirement. So for example, if your QoS requirement is k megabit per second, I need to ensure that on any link, these k megabit are available, and if yes, and I'm going to accept the call, I have to subtract this bandwidth, this bitrate, from the bitrate availability on each link, on each node on the path. Okay? Normally, we have some constraints as well in the CAC. Normally, it's not acceptable, it's not considered not acceptable to accept the call and reserve the resources for this call to satisfy it if this implies that you reduce, or even worse, you destroy the quality of already accepted calls or connections. So the agreement normally is that already running calls or connections or flows or user flows or whatever you want to call them should not be damaged, should not see a worsening of quality due to the fact that you accept a new call. Okay? A typical example of that, think about the telephone system. In the telephone system, we are willing to accept that the network may tell us you cannot make the phone call because I don't have enough resources, right? That's a blocking. I try to make a phone, I starting to dial a number, and even before I'm ending up the dial phase, I get a busy tone. The network tells me I don't have the circuit for you. You cannot make the phone call. That's absolutely acceptable. Of course, if it's happening very rarely, but that's acceptable. What is not acceptable is that while you are making a phone call, somebody is coming and tell you, hey, you have to reduce your bit rate, or you have to share your channel with your friend there because this friend wants to talk as well. This is absolutely not acceptable, right? Nobody would accept it in the telephone network. Whereas everybody is accepting that normally in the internet. That's what happens normally in the internet, right? That's absolutely acceptable there. But in the internet, we are not running CAC. We are accepting any call. So normally, when you run a CAC, the assumption is that already accepted call should not be damaged, should not be changed. This can be relinquished. You may say, OK, my network architecture, this may be acceptable. So I may go through a renegotiation phase with some calls, asking them if they are willing to reduce the quality. For example, you may ask to a user, OK, you are running a video conference with this given quality. Are you willing to accept a reduction in the bit rate, which means a reduction in the quality of the image that you will send through your video? For example, because I reduced the rate, how much you have to pay, so your cost will be reduced by 50% if you accept a 10% reduction in quality, something like that. That's possible. That goes through a renegotiation phase. So you run again a CAC, you go to the service interface, you run a signal. That's possible, okay? Many standards envision that. Practically, this is not normally done. It's too complex, and the advantage that you can get is not paying off. So normally, providers are not willing to do that, okay? Even in the architecture in which this is potentially possible. Of course, connection must be refused to avoid any overload or congestion. This is the basis of any CAC. Even a more simple one will for sure refuse any connection if the acceptance of this connection can create on that path a potential congestion or overload problem. Okay? Now, this algorithm is typically preventive. Why? You run it a priori. You run it before any data generation process starts. Okay? So that's normally a typical example of a preventive control algorithm. It may become reactive whenever you accept a renegotiation of this quality through what I said before. So for example, you can go back to an already accepted call and try to start a renegotiation process. Why you do that? Because there is something bad happening in your network, or you want to accept more users. You have a change in the network status, and that implies that you want to renegotiate. That's a typically reactive approach. So normally this is a preventive technique. It may become reactive in some cases if you accept to run this algorithm in this fashion. As I said, normally this is very rarely seen, very, very rare. Okay? Any question? Now, there is almost never a question that implies that either you understand everything with probability 0, or with probability 1 you are so bored and so little interest about this topic that there is no question. Okay, never mind. So let's have a break, short one, and then we will resume. And for those of you that arrived late, don't remember that at 2:30 there will be another class, 1 hour and a half in room 2I. Okay?